All right, here we have lecture 2.1. Now this is going to be a slightly different format. Normally I do a pencast, but here I'll be using the document camera to record a lecture. And this entire document that I'll be writing on is available on Folio, posted right before this video. So I highly recommend you either print this off or download it and reference it. I recommend you take notes on this handout as you watch this lecture. And also, this is the same packet that was passed out to those that attended class earlier this week. But if you don't have this pack yet, recommend you print it off. It's on Folio. Let's get started. So we'll open up with proportions. A proportion states that two ratios or fractions are equivalent. So a proportion will always be of this structure. A over B equals C over D. So whenever you're setting up a proportion, you want your units to match. So you want the numerator units to match and the denominator units to match. So if this is, I don't know, unit X on the left, then I would want unit X in the numerator on the right. And if I have unit Y in the denominator, then I would want unit Y in the denominator over there. So for example, the example of a proportion that's equivalent is if you're going 100 miles per every 2 hours, then that is equivalent to going 50 miles per every 1 hour. I think we can all agree that that's correct. 100 miles per every 2 hours is the same thing as 50 miles per every 1 hour. Notice the units in the numerators match and the units in the denominators match. Units must match across the numerator and denominator for the proportion to be equivalent. Naturally, if I had it, 1 hour per every 50 miles, then that wouldn't make any sense at all. And then a good tip for solving these is to use cross multiplication. But let's go ahead and dive into our first example here. So on a particular map, 1 inch represents 5 miles. You measure a distance of 9.25 inches between the two towns on the map. What is the actual distance? So we have 1 inch on the map per every 5 miles in reality. And we can set that up as a proportion to equal 9.25 inches on the map per every X miles because we don't know that unit. So once we have the setup done, we can kind of ignore the units and boil this down to a pure algebra problem. And cross multiplication is perfect for solving these proportions. So cross multiplication is exactly what it sounds like. It's just a method for solving proportions. 1 times x equals 5 times 9.25. So let me see here. Pull my calculator out real quick. So that's going to be a little over 50, I do believe. Let me go ahead and confirm that. 5 times 9.25. I'm sorry, a little over 45, I should say, and you get 46.25. And there's our answer. Let's go ahead and look at another example here. So a particular model car is built on a 1:12 scale ratio if the real car is 10 feet long. And how long is the model car in inches? So whenever you're working with a scale ratio, you can view scale ratio as a multiplier if you want, or you can set up a proportion. So there's multiple ways to handle scale ratio problems. I'll go ahead and view it as using it as a multiplier. So if it's a 1:12 scale ratio, that means for every 1 inch on the model, you'd have 12 inches in reality. For every 1 foot of model, you have 12 feet in reality. In other words, the real thing is 12 times the size of the model. So if the real car is 10 feet long, then the model car is going to be 1/12 of that, so you divide by 12. But if I just lost you, you can go ahead and set up proportion. So for every 1 unit in the model, we have 12 units in reality. That's our scale ratio right there. We don't know how large the model is, but we know the real thing is 10 feet in reality. So if we want to set up a proportion, it would look like this: 1 to 12 equals x to 10. We'll go ahead and solve that. So if we cross multiply, 10 equals 12x. Therefore, x equals 10 divided by 12. All right, now we want to be careful when you're solving a proportion. There is no unit conversion. So we know that when we do 10 divided by 12, that reduces to 5/6. That's in feet. So that's because this unit here was in feet. We did not do a unit conversion. So we need to convert that to inches. So if we want to convert that to inches, we simply multiply by 12. And there we get our value of, let's see here, 10. So it's a 10-inch model. And that's because I asked for it in inches, but the real thing is in feet. So you just want to be careful with that. In other words, the real thing has to be 12 times the size of the model. So if I have a 10-inch model, that means the real deal is going to be 12 times that length. Well, 12 times 10 is 120. It's 120 inches. 120 inches is 10 feet. So the math checks out. So you just want to be careful with the units there. So suppose your 6-foot friend is casting a 5-foot shadow. Nearby tree is casting an 11-foot shadow. How tall is the tree? So for every 6 feet in height, you have 5 feet in shadow. And we have an 11-foot shadow and unknown value in terms of height. So there's our proportion. We'll go ahead and solve that. So 5x equals 66. Divide both sides by 5. There we have it. That will get us the value we want. And the answer is 13.2 feet. So the tree is 13.2 feet tall. Now here's a popular or common application of proportions in baking. So we have 3 cups of milk per every 8 eggs. So then the question is, suppose we want to up this to where we use 12 eggs. We want to know how much milk we need. So there's our proportion. Notice we got units to line up. So use cross multiplication. So 8x equals 36. So divide both sides by 8, and that will get us to the solution, which is 4.5. So we would want 4.5 cups of milk. All right, so suppose you have 5 eggs in the fridge. Well, it's the same ratio. For every 3 cups of milk, we're going to use 8 eggs. Stand by here for a moment. There we go. So we'll go ahead and solve that. We're going to be using 5 eggs, so I know our answer is going to be less than 3 cups of milk. Cross multiplication, so 15 equals 8x. Divide both sides by 8, and there you have it. So that will get us here 1.875 cups of milk. All right, so let's go ahead and start talking about percentages. So the word percent literally translates to division by 100. So recall P percent equals P divided by 100. And just keep in mind, anytime you divide by 100, all you need to do is move the decimal place. So 70%, that symbol right there is a percent symbol. It literally means division by 100. So 70% means 70 divided by 100, which is 0.7. So, and that word of implies multiplication. So 70% of 700, that literally translates to 0.7 times 700. And that quantity of people said they prefer to watch football at home. So go ahead and multiply, you get 490. Looking at number 2, a particular class of 17 girls and 14 boys. What percentage of the class is female? So we need to figure out how many students there are in the class. So there's 17 girls, 14 boys. So that tells us how many students are in the class. Out of those, let's see here, 31 students. How many are girls? Well, that would be 17. So that's 17 out of 31. So if we multiply that here, we get, or I'm sorry, do 17 divided by 31, we get approximately 0.5484, which is approximately 54.84%. So a little over half the class is female, which makes sense. 17 over 31 is a little over half. So let's talk about percent increases and decreases. So this is essentially using percent markups and markdowns. So here, let's go ahead and look at some of these problems. But before that, let's discuss the following concept. If a quantity is marked up or down by percent, we use the following concept. It's going to be the original quantity plus or minus some percentage of that quantity is going to equal the amount after that markup or markdown. All right, of course, if it's being marked up, we'll use addition. If it's being marked down, we'll use subtraction. So let's look at this first example. An iPod is on sale at Target for $149.99. Sales tax is 7%. Find the price of the iPod after tax. So we want to make sure we don't confuse the original amount with the final amount. We know the original before the percent markup is $149.99. Sales tax indicates it's being marked up, so plus 7%. 7% is 0.07 of that $149.99. So when you're doing a percent increase or decrease, these two values are always the same. And from there, it's just a matter of using your calculator, which gives us 160. Rounding to the nearest cent, it would be 160.49 would be the cost after tax. Now compare example 1 to example 2. So here we have $200 to spend on groceries. Tax is 7.6%. How much can we spend before tax? We don't know how much we can spend before tax. We know it's less than $200. We know that, but we don't know that quantity. So in this case, our original is unknown. So we'll call it X. Don't know what it is. It is going up because it's sales tax. It's being increased by 7.6%, which is 0.076, times that unknown value. That tax is being applied to a quantity we do not know yet. But the idea is when we take that original amount and add sales tax, we want that to come out to $200. So there's our equation. So this one, we'll take a little bit of algebra. So you can see the nature of this problem is very different from the nature of example 1. Example 1 doesn't really require any algebra since you know the original value. Here the original value is unknown, so it does take a little bit of algebra to work towards it. So let's go ahead and solve this. We'll combine like terms. So 1x's plus 0.076x's is 1.076x's. And then we want to isolate the unknown value, so we'll divide both sides, and that will get us our answer. We'll go ahead and round it to the nearest cent. So 200 divided by 1.076 is 185.87. There you have it. All right. Number 3, a pair of pants is on clearance for $15 after 40% was taken off the original price. Find the original price. So this one's a little bit easier. It pretty much explicitly states we don't know the original price. So we'll call it X. Again, kind of going back up here, we don't know the original cost before the markup. It says it's on clearance after 40% was taken off. So we know it's a deduction, so it'll be minus some percentage of that original, in this case 40%, 40% being 0.4 times that quantity we don't know yet. And after that deduction, it came out to $15. So we'll go ahead and solve that equation. So 1x minus 0.4x's is 0.6x's. If you're uncomfortable with decimals, feel free to use a calculator. And this makes sense. If you deduct 40%, that essentially means you're paying 60% of the original price equals 15. Essentially what that equation is stating. Divide to isolate the unknown, and bada bing, bada boom, we get 25. So that tells us the original price was $25. Suppose a table is on sale for 26% off, sales price is $703. What was the original price? So that's again explicitly stating we don't know the original price. We'll call it X. It's gone down by 26%. And after that deduction, it came out to 703. So we'll go ahead and solve that. So 1x minus 0.26 x's is 0.74 x's. And then we'll just divide both sides by 0.74. As you can see, it's kind of the same in song and dance, solving these equations. It's always the same steps. And we get the value, $950. All right. Last example involving percent markup or markdown, number 5. So in 2004, the population of a large city was 45.9 million. This represents a 9.6% increase over the population in 94. Find the population in 94, and then round that to the nearest tenth of a million. So that 45.9 million is after the percent change, not before. So we don't know the original value before the percent change. So we'll call it X. We don't know what it is. It's been increased by 9.6%. Whatever that value is, it's gone up by 9.6%. So we don't know what that population was, but it has increased by 0.096 times that value. So 0.096 is 9.6% of that number, which we don't know yet. And after that increase, it came out to 45.9 million. All right, let's go ahead and solve it. So combine like terms. So x plus 0.096x combines to 1.096x. And then go ahead and divide both sides. You'll need a calculator here. So x is approximately 41.9. Let me double check that. I may have mistyped 45.9 divided by 1.096. Yep, 41.9, rounding to the nearest tenth. There you have it. Cool. All right, so let's go ahead and talk about comparisons with percentages. So let's discuss absolute and relative difference. So the absolute difference is the absolute change. This is computed via subtraction. This is computed via subtraction. So, a good example of an absolute difference is if my salary went from, let's say, $40,000 a year to $50,000 a year, then the absolute difference would be an increase of $10,000. So in other words, the absolute difference is computed via subtraction. So quick note here that you want to be aware of. Positive, an absolute positive difference implies an increase, whereas a negative value, a negative absolute difference would imply a decrease. That helps you get the order of subtraction correct. So here, in order to compute this, I did 50,000 minus 40,000, not 40,000 minus 50,000. I did 50,000 minus 40,000 because I know that there has been an increase in my salary, so this number should be positive. So the absolute difference is just computed via subtraction. The relative difference is the absolute difference represented as a percentage. So if we take that absolute difference and we want to represent it as a percent change, we would call that the relative difference. So the trick here is you're always going to divide by the value you subtracted. So, i.e., if we go back to my salary went from $40,000 to $50,000. So the absolute change would be 50,000 minus 40,000. Nope, there's zero there. Because it's a $10,000 increase, and whatever you subtract by, that's what you'll divide by. So if we compute that real quick, that's going to be 10,000 divided by 40,000, which is 0.25, which tells us that we have had a 25% increase in salary. And that is the relative difference. So in order to compute the relative difference, you take your absolute difference divided by the value you subtracted, or what many texts refer to as the reference value. So let's go ahead and practice with this a little bit. Last quarter, Xerox stock increased from $6 to $15. Compute the absolute and relative change. Let's do the absolute first. So we want to ask ourselves, has it gone up or down? If it's increased, we should get a positive number. If it's decreased, we should get a negative number. Since it has increased, we should get a positive result. So when deciding whether to do 6 minus 15 or 15 minus 6, we know it's going to be 15 minus 6 because there has been an increase, which gets us 9. So in other words, remember, the numbers are useless in this. You can make sense of them. What does this 9 represent? Well, it tells us that stock price increased by $9 per share. That's what that's saying. Stock price increased by $9. Now let's represent that change as a percentage. So in order to compute the relative difference or the relative change, we take the absolute change, which is 15 minus 6. So we're just taking what we did for the absolute change, and then we divide by whatever we subtracted. In this case, 6. So that would be 15 minus 6 divided by 6. So that's 9 divided by 6. So that reduces to 3/2, which is, in other words, 1.5. In other words, 150%. All right. So that tells us that it's a 150% increase in stock price. So we can represent the change in absolute terms, or we can represent it in relative terms. Representing it in relative terms is essentially representing it as some percentage. Let's get some more practice with this. So go ahead and flip over to number 2 in your packet. 3 years ago, your TV is worth $1,000. Today, it's worth $300. Find the absolute and relative change. Let's start with the absolute. So we want to determine, has it gone up or down? It was past tense worth 1,000. Today, it's worth 300, so it's gone down. So when trying to determine the order of subtraction, it's been a decrease, so we should get a negative number. In order to guarantee a negative number, we're going to be doing 300 minus 1,000, which is negative 700. Note that we get a negative value there. It's very important. The negative indicates a net decrease, which tells us that it has decreased in value by $700. Now let's compute the relative change. So we take this expression, 300 minus 1,000, and if we want to compute the percent decrease, we simply divide by whatever it is we subtracted. So we subtracted by 1,000, that's what we're going to divide by. So that's going to be negative 700 divided by 1,000, and that is negative 0.7. In other words, negative 70%. We still get a negative number because there's still many net decrease. So we can also say it decreased by 70% of its value. As it was at $1,000, now it's at 300. So going from 1,000 to 300 is a net decrease of $700, which is 70% of the original value. All right. Now, that involved time, so we can also do relative comparisons, not only across time, but between two different products or objects. So you got a Mercedes SUV, which is $50,000, and a Lexus SUV, which is $40,000. Let's go ahead and do a quick comparison. So if we want to do this in absolute terms, we can do, so here the order doesn't matter so long as we understand our conclusion. If I do 50,000 minus 40,000, I get $10,000, and it's positive, so that means an increase. So in other words, if positive 10,000, we can say the Mercedes costs $10,000 more than the Lexus. Now, if we want to do this in terms of relative, in terms of a percent change, we would do the same thing we did before, which is take the absolute change and divide by whatever it is we subtracted. So that's going to be 10,000 divided by 40,000, which gets us 25%. So in other words, the Mercedes costs 25% more than the Lexus. That would be a correct statement. But what if we did the other way around? So, or there's another way we could do it. Another way we could do this in terms of absolute change is we can do the different direction, 40,000 minus 50,000, which is negative 10,000. And that's essentially saying the Lexus is $10,000 cheaper. Okay, well, duh, that's not a surprise, but here's where it gets interesting. In terms of the relative amount, if I do this way, I'm not going to get 25%. If I compute it in terms of this direction, I get negative 0.2, which is negative 20%. So we can say the Mercedes costs 25% more than the Lexus, or we can say the Lexus is 20% cheaper than the Mercedes. So those are different percentages. So we got to be very careful here when we're comparing two objects. When I say the Mercedes costs 25% more than the Lexus, I'm saying, hey, take the price of the Lexus and increase it by 25%. Well, the price of the Lexus is $40,000. Well, 25% of 40,000 is 10. Okay, that's a $10,000 difference. Makes sense. But if I say the Lexus is 20% cheaper than the Mercedes, what I'm saying is, hey, take the price of the Mercedes and knock off 20%. Well, 20% of the Mercedes is $10,000. So you have to be very careful here. You can actually see it's two different percentages depending on which way you do the comparison, right? So you got to be very, very cautious here. For example, I cannot say the Lexus is 25% cheaper than the Mercedes. That would be an incorrect statement, because then I'd be saying the Lexus is 25% cheaper than Mercedes. That means they knock the Mercedes price tag off by a quarter. That's not correct. You'd be off by $2,500. So you want to be very careful here. Context matters. So it's not just about mindlessly running through numbers. You really do need to understand what the numbers represent. So number 4, we'll go ahead and move on. This one is very, very similar to number 3. So in the interest of time, we're going to go ahead and move on to my favorite part of this lecture, how percentages can deceive. As you can see with this Lexus Mercedes example, you can see sometimes they're a little bit tricky. So percentages often confuse people, which means they can often be used to manipulate people. So let's look at this first example. So here we got an example where Jimmy agreed to a 10% pay cut, but then gets a 10% pay raise. So if you get a 10% cut, then a 10% raise, initially you might think you're breaking even. And that's the question. If you get a 10% cut, then a 10% raise, will you restore your original salary? Well, let's find out. Let's make up a number. So suppose salary is, let's go with $40,000. Suppose salary is $40,000. Well, then you get a 10% cut. So that means your $40,000 is being subtracted by 10%, which is 0.1 of your 40,000. And if we do that, we get $36,000. So if you get a 10% cut and you're at $40,000 salary, that means your salary dropped to $36,000. And then you get a 10% raise. Okay, so you were at $36,000 when you got the raise. It's increased, so plus 10% of the $36,000. And let's type that into the calculator. And you can see that you're not going to get the same value here. We're not going to get back to $40,000. We're going to be at $39,600. So the question was, will the pay raise restore Jimmy's salary? No. He'll be at a loss. So if you take a 10% cut, then get a 10% raise, you're going to be operating at a loss. Now the next question is, well, how much of a loss are you going to have? And initially you might say, well, his salary is going to be $400 less than where it was. Well, that's not factually correct. We made up the $40,000. We made that up to just kind of play with the numbers. We don't know what Jimmy's salary is, so it's impossible to compute the absolute difference. But what's fascinating is we can actually compute the relative difference. So started at 40,000, ended at 39,600, so that's a net decrease. So when we compute the percent change, we want it to be negative. So we're going to subtract in this order. Kind of goes back to what we were doing with the Xerox stock, the TV, and the Mercedes problem. With the relative change, we have a net decrease, so that'll be the order of our subtraction. You always divide by what you subtracted, and you're going to get negative 0.01, which is negative 1%. So actually, if you take a 10% cut, then get a 10% raise, you're going to be at a 1% loss no matter where you were at. If you were at a $40,000 salary and get a 10% cut, then a 10% raise, you're going to be down by 1%. If you were at a $40 million salary and you get a 10% cut and a 10% raise, you're still going to be down by 1%, no matter what. If you have a 25-cent salary, you're getting paid a quarter a year. If you have a 25-cent salary, you get a 10% cut, then a 10% raise, you're still going to be down by 1%. So this is where the relative difference or relative change can be useful. We can compute the relative change even if we can't compute the absolute change, just by playing with some numbers here. So let's look at this example. So I'll let you go on and read that. Again, you should be paying attention to your own packet. So we'll suppose we get a 60% cut or drop followed by a 75% increase. So are you going to be 15% ahead? Well, let's find out. So let's go ahead and make up a number. So I always like using the number 100 because it makes these percent problems easy. So it's not a salary, it's an investment. So suppose your investment is worth $100. All right, this will make the numbers easy. $100. So then you got a 60% drop. So that 60% drop indicates that you were at 100, it's gone down by 60%, which means we're now at $40. This is why I like picking 100, makes these computations easy. Then you got a 75% increase, or let's call it a raise. Okay, well, your investments dropped to $40, but then they increased by 75%. And there we get 70. Wait a second, we started at 100 and we ended at 70? Yeah, you're still at a loss. Still at a loss. If you take a 60% decrease, then get a 75% raise, you're still operating at a loss, actually. So no, you're not 15% ahead, you're still at a loss. Now, it says here, compute the actual percent change. Well, we know it's negative. So that'll be our order of subtraction. It's decreased by $30. Whatever you subtract by is what you divide by. That's why I like starting off 100, makes the division really easy. So negative 30 out of 100, that's negative 30%. If you take a 60% drop and get a 75% raise, you're still going to be 30% lower than where you started, actually. You're still going to be at a loss of 30%. So as you can see, percentages can be a little bit tricky sometimes. Let's look at another example where percentages can be tricky. So here you got shooting performance of 2 players in a basketball game. Let's go ahead and complete the table. So in the first half, Kevin made 4 out of 10 baskets. So 4 out of 10. If we write that as a percentage, that's 40%. So Kevin made 40% in the first half. Kobe is 1 out of 4. So if you compute 1 out of 4, that's 0.25, which is 25%. So yeah, 25% was the shooting percent. That's the first half, 40% and 25%. Then Kevin, 3 out of 4. If you do 3 divided by 4, that's 75%. If you do 7 out of 10, that's 70%. All right, cool. So there's all the percentages. So who had the higher shooting percentage in the first half? Well, Kevin was a 40% shooting percentage, and Kobe was 25%. So Kevin had a better shooting percentage in the second half. Who had a higher shooting percentage in the second half? Well, it's 75 versus 70. Kevin still wins. So Kevin had a higher shooting percentage in the first half, a higher shooting percentage in the second half. So who had the better shooting percentage overall? Well, Kevin won in the first half and he won in the second half, so that means he won overall, right? Well, let's find out. Let's look at the overall. So overall, let's look at Kevin. So overall, Kevin made 4 baskets in the first half and 3 baskets in the second. So Kevin made 7 baskets out of, he had 10 attempts and 4 attempts. So he made 7 out of 14 baskets. Okay, so overall, that's 50%. Whereas Kobe, if we go back and look at the table, Kobe, he made 8 out of 14 baskets. So he had 8 baskets altogether out of 14 attempts. He actually barely won. So we want to go ahead and compute that real quick. We actually see that's approximately 57.14%. So actually, Kobe had the better shooting percentage overall. So Kevin was better in the first half, Kevin was better in the second half, but Kobe was better overall. So as you can see, sometimes you just got to run the numbers. Now, why is that? Because, well, if you look at the number of attempts, Kevin had way more attempts in the first half than Kobe did, but Kobe had way more attempts in the second half than Kevin did. So since they really don't have the same number of attempts in each half, that can distort things. So let's look at something where we get even more of a distortion. So here's data pulled from an old textbook. So this is, a few years old. It's from an old quantitative reasoning textbook. So this is quite dated, but let's go ahead and look at this data. So a mammogram is an X-ray procedure often used to detect breast cancer. A positive mammogram is supposed to indicate a malignant tumor, which is bad. Right? A malignant tumor is a cancerous tumor. A benign tumor is fairly harmless. Here are the results from 10,000 mammograms. So let's briefly describe the following. So a true positive means a positive test result on a malignant tumor. In other words, the test was correct. So it's a positive result that is true. So in this case, we have 85 true positives. A true negative is a negative result on a benign tumor. So it's a negative result that is correct. Like if you test negative, that's supposed to be representative of a benign tumor. So if we look at our benign tumors, 8,450 tested negative. So when we say true positive or true negative, that means the test did what it was supposed to do. The test was correct, right? If it's a true positive, that means that person tested positive and they actually have a malignant tumor. If it's a true negative, then that means they tested negative and they do not have a malignant tumor. The scarier ones are when the tests are wrong. So unfortunately, in the real world, tests are not always correct. You can have a false positive. A false positive is a positive result on a benign tumor. All right. So in other words, it's a positive result that's wrong. If you test positive, you're supposed to have a malignant tumor. But sometimes you test positive when you don't have one. So there's 1,485 people in this case. All right. And the false negative, this is the scary one. This is a negative result. That's wrong. So in other words, on malignant. All right. Okay, so in that case, that's 15 poor souls. This is the scariest case. So you test negative, you think you're in the clear. Well, the test was wrong. You actually do have a malignant tumor. So the idea with true is these are the correct tests. These are on the incorrect test, right? So you can have incorrect positives and incorrect negatives. You can also have correct positives and correct negatives. And there are the numbers from the table. So what percentage of malignant tumors were correctly identified? So how many malignant tumors do we have in this data set? So out of these 10,000 cases, 100 had malignant tumors. Let me try and zoom out here so we can see the whole table. There we go. That's better. So we had how many malignant tumors were correctly identified? There were 100 malignant tumors. How many were correctly identified? Well, a malignant tumor, if you have one, you're supposed to test positive. Well, out of these 100, 85 tested positive in this one mammogram. So it's 85% correct or accuracy. What percentage of benign tumors were correctly identified? So how many benign tumors did we have? Well, we have 9,900 benign tumors. And then out of those, how many got the test result they were supposed to get? Correctly identified. Well, if you have a benign tumor, you're supposed to test negative. Well, these 8,415 people tested negative. So you type that into a calculator and you get 85%. How accurate are the mammograms? Well, in the case of malignant tumors, they're 85% accurate. In the case of benign tumors, they're 85% accurate. Therefore, you can conclude that these mammograms, at least according to this data set, are 85% accurate. Okay, makes sense. So then the million-dollar question. If you receive a positive mammogram, then what is the probability that your tumor is malignant? Right, because you go get a mammogram, you test positive, that's very scary. Oh no, I tested positive, I've got breast cancer. Well, do you? What's the probability that if you test positive, you have breast cancer? So is it 85%? The test is 85% accurate. Therefore, if I test positive, there must be an 85% probability that you have cancer, right? Not quite. So let's look at, suppose you get a positive mammogram. Well, how many positive mammograms were there? Here's the positive mammograms. There were 1,570. There are 1,570 positive mammograms. Out of those 1,500, well, almost 1,600 people, how many actually had a malignant tumor? 85. What? Yeah, that's correct. Out of 1,570 positive mammograms, 85 of them tested positive. So that tells us that's approximately 5.41%, at least according to this data. So the test is 85% accurate according to this data, but that results in you having a 5% probability of actually having a malignant tumor should you test positive. Why? Why? This can't be right. Something's wrong here. Well, look at the data set. And you can see why this occurred. You have 100 malignant tumors and 9,900 benign tumors. So you have a huge disparity between these two sets, right? This set is, there's far, far, far more benign tumors than there are malignant tumors. So yeah, the test is going to be wrong 5% of the time. But 5% of 100 is much, much, much smaller than 5% of 9,900. You're like, well, this is a horrible study. This is skewed. This is some crazy conspiracy theory. Not quite. This occurs naturally. Turns out most tumors are actually benign. That's why you see this divide here. All right, this is a natural divide which is causing this massive skew in the result. This is the reason why if you test positive on a mammogram, do they wheel you over into chemotherapy and immediately start treating you for cancer? No. If you test positive on a mammogram, you're still in the diagnosis stage, actually. Now, that is cause for concern. All right. If you test positive, that's not a good thing, but that doesn't necessarily mean you have cancer, actually. They're going to do more mammograms or they're going to move on to a biopsy. Biopsy is a tissue sample. And it's not, biopsy is not treatment. They're still trying to figure out if you have cancer or not. This phenomenon is tied to Arrhenian math, probability to be specific. It's tied to something called Bayes' theorem, which I'll send out a video on. It's quite fascinating. And I think it's pretty relevant with coronavirus these days. So I'll send out you a video on Bayes' theorem, which involves explaining the mathematics behind why we have this massive disparity, how we can have an 85% accurate test result in a 5% probability of you actually having the disease, even if the test is 85% accurate. So let's actually go into practice with this phenomenon in the last example. So suppose a test for a disease is 95% accurate, all right, for those who have the disease and 85% accurate for those who do not have the disease. So that's actually a little bit more realistic. So, typically the accuracy rating is going to be different for people of different demographics and different conditions, and, and what have you. There's so many variables in play when you're trying to do this. It's very, very complex. But what we're dealing with here is suppose the accuracy is different for people who have the disease than it is for people who do have the disease. So if you have the disease, the test is 95% accurate. If you don't have the disease, the test is 85% accurate. A positive test result is supposed to indicate the patient has the disease. Within a sample of 4,000 patients, suppose you have an infection rate of 2%. So 2% actually have the disease, complete the table below. So 2% actually have the disease in this population. That's 2% of the 4,000, which is 80. Off to the side, if you're confused where that came from, I did 2% of the 4,000 is 80. All right, because 2% of these 4,000 people have the disease. That means you got 80 people with the disease. Well, if 80 people have the disease, then that means you've got, let's see here, 3,920 who do not. All right. And you can get that just from subtraction. All right, because these two numbers better add up to 4,000. So if 80 people have the disease, 3,920 people do not. So let's go ahead and start running the number of testing results. So the test for those who have the disease is 95% accurate. So for this column, the test is 95% accurate. For this column, the test is 85% accurate. So if you have the disease, you're supposed to test positive. And the test will be correct 95% of the time, which means 95% of these 80 people are going to test positive. 95% of 80, which is, I wish I brought my calculator. I'm using my phone right here, which is 76. So 76 people are going to test positive, which tells you 4 are going to test negative. Those 4 are the scary ones, right? Because they have the disease and they tested negative. So the test was wrong. They take the test, they test negative, they think they're okay. When they're not, they actually do have the disease. Now let's look at this. 85% do not have the disease. If you do not have the disease, no disease, you're supposed to test negative. And the test is 85% accurate. So most of these people will test negative. All right, the test is correct most of the time. In fact, it's correct 85% of the time. So we do 85% of those 3,920 people, which is 3,332 will test positive. Test negative. And then we can just use subtraction to figure out how many tested positive, which is 588. And then we can take the totals. So 76 plus 588 is 664. And then we do 4 plus 3,332, which is 3,336. And here's how you can check your numbers, actually. If you add these two numbers, you should get back to 4,000. That's a good way of determining if you got your chart fairly well set up. So let's test that. They add up to 4,000, so that's a good sign that our chart's looking good. So how many true positives are there? So how many people tested positive and the test was correct? So there's 76 who tested positive that have the disease. There's 588 people who tested positive and are clean. Well, if you test positive, you're supposed to have the disease. So there's 76 people who tested positive and do indeed have the disease in this population. Of those with the disease, I'll pause there. So how many people have the disease? That's 80 people. Of those with the disease, what percentage tested negative? Well, there's 80 people that have the disease. 4 of them tested negative. 4 out of 80, that's 5%. So in other words, if you have the disease, 5% of them are going to test negative. Makes sense because the test is 95% accurate. Now here's where it gets fascinating. Out of everybody who tested negative, how many actually have the disease? So how many tested negative? Well, these 4 people tested negative. And these 3,332 also tested negative. So that means you have 3,336 people who tested negative. How many of those actually have the disease? 4 of them. Okay, that's going to be a tiny percentage. That's going to be approximately 0.12%, less than 0.5%. So in other words, if you test negative, what's the chances you actually have the disease? Very low, very low. So that's good news. If you test negative, then the probability is definitely in your favor that you're okay. That you're okay. How many people, suppose someone tests positive, what's the probability they actually have the disease? 95%? Well, not quite, because most of the people don't actually have the disease. So this is causing a disparity in the data, which will kind of make the percentages a little bit tricky here. So how many tested positive? All right. Suppose someone tests positive. How many people tested positive? 664 people tested positive. Out of all those people that tested positive, how many actually have the disease? 76 out of those 664 have the disease. So that's 76 out of 664, which is approximately 11.45%. 11.45% actually have the disease. So assuming there's a single test and we're not doing multiple tests on one sample, that's the best way to correct for this disparity, right? You'd assume that if someone tests positive, that there's a very high probability that they have the disease. In a singular test, we see that's not the case. So the good news is those in the health sciences are aware of this phenomenon. It's tied to something called Bayes' theorem, where the math can be tricky. And it's whenever you have a disparity in your data sets. Now, this disparity can often occur naturally. Like it's a natural disparity that most people don't have the disease. So you just need to be aware of that when you're testing. It basically means you're going to have a skew in your data that you have to be aware of. And there are ways of mathematically remedying this. For starters, if you are testing, you don't take a single test on one sample. You can actually take multiple tests on a sample. It's one way of working around it. But what I'm trying to get at with these examples is the plot is more complicated than you think. All right, the plot is more complicated than you think, and you really, really do need to be careful when you start playing around with percentages. Anywho, on that bombshell, we're done with the lecture. Have a wonderful day, and shoot me an email if you have any questions.